Alright, so let us write down now the Taylor series expansion for those differential operators. So let me redraw the grid for you. So this is the x-axis, this is the y-axis, and I am just drawing a section of the grid. We are going to talk about these nodes as ij, and since this is the x-axis, this node is going to be I plus 1 and j, whereas the one on the left is going to be I minus 1 and j. Likewise, I can go up and down. So this node is going to be I and j minus 1, whereas this node is going to be I and j plus 1. Okay. All right, so let's write down the Taylor series expansion. So first I write it for u at x plus h comma y, and this I would like to write in terms of the expansion around the point uxy and only talk about the expansion along x. So this would be simply u comma x, of course evaluated at xy, times h, plus I would have 1 over factorial 2, the second derivative evaluated at h square, plus 1 over factorial 3 of u comma x x x evaluated at xy times h cube, and of course higher order terms. Likewise, I could write down u of x minus x and y, and this again I expand around uxy. So now I would have a negative sign. So I have this grid in mind. So I am trying to write down what is the value of u at I plus 1 in terms of the value at I, and also what is the value at ui minus 1 in terms of this value. So that's what I have in mind. And again a negative sign here. And higher order terms. So let me call this as my equation C and this as D. If I do C minus D, okay, then you will notice I will be able to get rid of these values, and I should be able to estimate what is my slope u comma x. So and I will also take an approximation by dropping my higher order terms. So u comma x at x y, which is actually this term, I can approximate this with u at x plus h comma y minus u x minus h comma y divided by 2h. Okay. And if I do C plus D, so notice by deriving this equation, which let me call this as E. Okay, so I have just subtracted D from C. These two terms cancel out. This is what I have on the left hand side, and again these terms cancel out, and I would have twice of these terms, the addition of these terms. but when I divide by h, then I am going to get left h square. So I am actually neglecting terms of the order of h square times, of course, a constant which would be the third derivative. So that's the error in estimating the derivative, the x derivative at xy, and it has, I have basically thrown out terms like h square and higher orders. If I add c and d, then you will notice I can actually, I get rid of these terms, and I should be able to get an estimate of u comma xx, which is, so let's do that. So if I add them, then these terms drop out, and I get sum of these and minus these terms, and I can estimate u comma xx. So let me write that down for you. So this would be u of x plus h comma y minus twice u xy plus u of x minus h comma y, and this whole thing divided by h square. And of course, again I am neglecting some higher order derivatives, and you can figure out what they are. Okay? So I am going to call this as f. So notice, if I want to estimate the x derivative, I can use equation E. If I want to estimate the second derivative, then I can estimate using equation f. So this is for u comma xx. I can do a similar thing if I want to write down u comma yy at xy. This I can approximate as u of x y plus k, because now my spacing, so recall this spacing is h and this spacing is k. So now I can go in the y direction. So I have this minus twice u xy plus u of x y minus k divided by k square, and of course I have incurred some error. Let me call this as g. If I add g and f, then I can get the sum of u comma xx and u comma yy, which actually is my Laplace operator. So u comma xx xy plus u comma yy at xy can be approximated as simply the sum of g and f. And you will notice I can get various terms. So let me use now the notation that we have formulated here. So I will replace this x plus h as I plus 1 j. This would be ij. This is I minus 1 j. Likewise, this quantity would be I j plus 1 I j, and this is I j minus 1. Okay. So this here actually corresponds to u comma xx plus u comma yy, but evaluated at ij, this whole quantity. So I could write this down as u I plus 1 j minus twice u I j plus u I minus 1 j divided by h square plus the contribution from u comma yy, which is u I j plus 1 minus 2 u I j plus u I j minus 1 divided by k square. Okay. What I can now do is, I can also choose h square and k square to be identical. So that's up to me. If I want to simplify it further, I can say, well, my grid spacing along x and y direction are same. But that's purely my choice. In any case, if you remember, this from my differential equation was supposed to be f of a quantity at this ij. So maybe I simply write this as fij. Okay. So this now is my stencil. So what I can now do is that on this grid, at each point, I had the Laplace equation or the Poisson's equation. I can actually replace that with this difference equation. Okay. So you will notice that at each point ij, I am actually able to write the equation in terms of the unknown here as well as its 4 neighbors. Okay. And that's what you can see from this stencil. So I can write this equation at all the nodes, and suppose I have n unknowns, I can generate n equations and I can rearrange them and solve for them. Alright, so let's take a simple example. And understand how this works. So let me set up this problem for you, a very simple problem, and show you how this method works. So let's say this is my x-axis, this is my y-axis, and I am interested in the temperature distribution on this plate. Okay, I will consider a small discretization wherein I have 4 nodes in the x direction and 4 nodes in the y direction. So overall I have 16 nodes. So this is 4 by 4, which is 16 nodes. The boundary conditions are the following. On this boundary, it's a Dirichlet problem, so I am going to specify that my u is 100. On this boundary as well, I will specify that my temperature field has a value of 100. And on this boundary as well, let me again put it as u equal to 100. But on this boundary, I have a lower temperature field, and let me say that is 0. Okay. So the challenge is I am supposed to find out the temperature field inside, but because I have used only 16 nodes, so I already know the value on the boundary nodes and only 4 remain. So value of u is unknown at only 4 nodes. Let me number these nodes. So I will number these nodes as, for convenience, this would be 1, 1, this is 1, 2, 1, 3, 1, 4, this is 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, 2, 3, 3, 3, 4, 4, 1, 4, 2, 4, 3, 4, 4. Okay. So the values that are unknown are u22, u23, then u32, and of course u33. All other values of u are known to me. So I would like to solve the Poisson's equation. In fact, I would like to solve the Laplace equation. So let me assume f is 0 inside, there is no source term, and I just want to estimate the value of the temperature inside. Let me say this value is x equal to 0 and this is x equal to 12. So I am using HS3. Similarly, I will take y equal to 0 and this is y equal to 12, and I will also take k equal to 3. Okay. All right, so let's set this up. If you recall, the stencil that I have is the following. So I am solving this problem u comma xx plus u comma yy equal to 0, and I can use the stencil which I have derived, and that would be simply if I use h equal to k. So I can put h equal to k, and then these values simply become that u I plus 1 j plus minus 4 uij plus ui minus 1 j plus ui j plus 1 plus ui j minus 1. This actually is equal to 0. Okay. This is the stencil that I get from what I have already shown you. Okay. All right. So now what we will do is we will write equations at the 4 nodes, and these nodes are the ones that I have darkened, because these are the only points where we do not know the values. I already know the values at all other nodes, so there is no point in writing equations at those. I only write them here. Okay, let us begin with 2, 2. So at the node 2, 2. If I write the value if I substitute for the values in this stencil, then what you will know is that it uses all these neighbors. Okay, so it uses the neighbors to the left, to the right, top and bottom. And you will notice that many of them actually lie on the boundary. So these values are known to me, and only these 3 values are unknown. Okay, so what I can do is, when I substitute it in this equation, the values which are known to me, I can take them to the right, okay, and only leave the unknown values. All right, so let's write down the equation here first. So u21 plus u12 plus u23 plus u32 minus 4u22 is 0. Okay, that is my equation at 2, 2. But as I said, u21, this actually is equal to 100. Similarly, u12, this value is 100, and the others actually I do not know. So these I would transfer to the right hand side and only leave these 3 unknowns over here. Let us now move to node number 2, 3. Again, here it would be using the 4 neighbors and of course 2, 3 itself. So let me write that down. So this would be u22 plus u13 plus u24 plus u33 minus 4 u23 equal to 0. And as I said, U13 and U24, U13 and U24, these both have a value of 100 each. So they can be transported to the right hand side. We now come to node number 32, this one, and I am going to write this directly for you. So U31 plus U22 plus U33 plus U42 minus 4 times U32 is 0, but then the values 31 and 42, these values are specified. Notice U31 is 100 but U42 is 0. So U42 is 0 and this value is 100. Similarly, I can write down the equation at the node 33, and that would be given as U32 plus U23 plus U34 plus U43 minus 4 times U33 equal to 0, and I can again substitute for the boundary values. So U34 is 100 and U43 is a value 0. Okay? And what you would now get is a system of 4 equations and 4 unknowns. And one can actually solve for them. Okay? And I can now get the values, and that would be my approximate solution. Okay? If I take a larger number of grid points, so this was a grid system of 5 by 5, I could very easily expand it to larger number of grids. So suppose I had 1000 grid points in the x direction, 1000 in the y direction, then I would have a large number of unknowns, and I could still form this equation on a computer and solve for them. Okay? Of course, the effort required would be larger, and perhaps I would get a better approximation. All right. One thing that I would like you to notice is the following, that these values are never used. Okay, so note corner values are not used, which is a little bit strange. In fact, some of you can already notice that there is a singularity here at the 2 corners, because the temperature changes from 100 to 0. So it's almost like a plate which is dipped in boiling hot water at these 3 edges, and this one is in contact with frozen ice, okay, at 0 degree centigrade. And these values are, it's not clear whom they should belong to. Should they belong to the edge with 0, or should they belong to the edge with 100 degrees? Okay, so that's a little bit tricky. But this numerical method, very strangely, doesn't care for it at all. In fact, when I write down the equation here, I only use these values. Similarly, when I write the equation here, I use only these values, and the corner values are not used at all. It is possible to design methods where the corner values would also be useful, and then this would become very tricky as to which values should go in the boundary condition. But that's really not a problem of the numerical method. That's actually a problem of the way the problem statement has been defined. Okay? And numerics cannot resolve the ambiguities in the mathematical formulation of the problem. So I hope you have got a flavor of how to handle numerically the Dirichlet problem based on the Laplace equation. I now want to address a little bit more complexity into that approximation. So let me write down the stencil for you again. So this is the Dirichlet problem for the Laplace equation. And we found out this is u I plus 1 j plus u I j plus 1 plus u I j plus 1 u I minus 1 j plus u I j minus 1 minus 4 u I j, this is 0. And the grid is something like this. So this is ij, this is I plus 1j, this is I minus 1j, this is I j minus 1 and I j plus 1. Okay. Now please notice that when I write down this equation and I have a large number of grid points, then in each equation I am going to have unknowns which are the neighbors, these 4 neighbors. Okay. So when I write down so many equations, then each equation has a number of unknowns, essentially 5 of them. But then as I go to the left or to the right or up and down, their location actually changes. So this becomes a fairly complicated equation system. It's sparse in the sense that if I write down the equation at this point, then there are only 4 or 5 unknown values in the left hand side and the other entries are 0. So it's a sparse matrix, not a full matrix. Now what is well known is that typically these equations are a little bit easier to solve, okay, if I have a tridiagonal system. So tridiagonal matrix equations can be solved efficiently. So those of you who are not familiar with what is a tridiagonal system, so suppose I have this matrix A, this is my vector x and this is my vector b. If I have entries only along the diagonal and all others are 0, that's of course a diagonal matrix. If I have a system where I have the diagonal is non-zero and one entry above the diagonal and exactly one entry below the diagonal, they are non-zero, but all others are 0, then this is a tridiagonal system. I can also talk about a pentadiagonal, wherein in addition to these 3, I could have 1 each on the upper and the lower triangle which are non-zero. So that would become pentadiagonal. So tridiagonal matrices are easy to solve, and what some people have figured out is that you can actually use the tridiagonal system by making some approximations to solve this equation fairly efficiently. And I wanted to describe that innovation to you, okay, and we will be using that later in the course. So I want to describe to you the ADI method. So the ADI method is the alternating direction implicit method. Okay, and we are going to use an iterative approach. So here is what we are going to do. As I showed you in the example earlier for the 4 by 4 equations, we had this Ax equal to b, so you would get a matrix with 4 unknowns. X would have dimension of 4, and then one can use a solver to get the solution. Now suppose I have a million equations, okay, and it is not possible for me to solve this system directly. Can I come up with an innovative approach to solve this iteratively but in a more easy manner? And that's what the ADI method allows us to do. So it's a very smart approach. Essentially what it does is it realizes that if I can freeze the values in the column, then these 3 values in a row, they can form a tridiagonal system. On the other hand, if I look at the values only along a column and freeze the values along the row, then these 3 values in a column, they can form a tridiagonal system. So this method is very innovative. It essentially iterates by freezing alternately rows and columns. And let me show you how it does that. So this was developed by Peaceman and Rashford. So the purpose of my showing you this method is not so much about the details, but about the innovation that one can use in these systems. So suppose U, I, J, M are known, and U, I, J, M plus 1 are to be formed. So I am going to use M as the iteration counter. Okay. So M is the iteration counter. So we start with some guess values, and we are on iteration number M, and at that level we know everything about the solution, and we just want to improve upon the solution, and the improved solution is M plus 1. Okay. So we are going to, let me call this as A. So A is approximated as so in the first iteration, I am going to do the following: U I minus 1j at iteration M plus 1 minus 4 U I j at M plus 1 plus U I plus 1 j at M plus 1. So I'll assume that these are unknowns. Okay, so out of these 5 values, the I plus 1 and the I minus 1 and of course the ij, they will be assumed to be unknowns. So basically in this row, and I'll assume that these are frozen, and I will use them from the M iteration level. So therefore I will transfer I j plus 1, essentially this value, and the j minus 1 values as the known values to the right hand side. So these I am going to simply write as minus ui j minus 1 at the level M minus ui j plus 1 at the level M. And therefore I would get a tridiagonal system, and this is fairly easy to solve. Of course, in the real matrix, all these were supposed to be at the same level, and therefore they should have been solved together. So in that sense, it's an approximation. So this I call B, and then in the next iteration, when I go to level C, which is at M plus 2, then I alternate. Now I am going to say that my columns are to be iterated, but the row values are frozen. So let me write that down for you. So I am going to now say ui j minus 1 are at M plus 2 minus 4 uij, these are at M plus 2, and likewise here I write ui j plus 1, these are at level m plus 2, and now the row values are frozen. So these become minus ui minus 1 j at m plus 1. So I am at the iteration level m plus 2, which means m plus 1 is the earlier iteration, and similarly ui plus 1 j at m plus 1. Okay. Again I have a tridiagonal system. Okay. And then I repeat this, so I keep alternating between rows and columns, and hopefully I would converge to the correct solution. So the idea is that we iterate till we converge. Now the question is, what does convergence mean here? Okay. Of course we are going to look at it in a little bit more detail later on, but I just want to give you a very average idea about this. So the hope is that as we keep iterating, we are going to get closer to the solution. How do we monitor that? So there are two things we can look at. So one is uij value. If I look at m and uij at m plus 1, how different are they? So the hope is that as I keep iterating, I would eventually get to the exact solution in the sense of exact solution of Ax equal to b, and therefore my solutions would stop changing. Okay, but still that's not enough. I should really look at Ax minus b. Okay, so if I look at this as the error, so this is the equation I was trying to solve. This is a stencil for the Laplace equation. This should be 0. So when I substitute finally, so here x is same as u, so if I substitute for u, and I should get close to a 0 here. So these are the two conditions. So this is based on the residual, and this is actually based on the increment, and we are going to talk more about this later on. Can we improve the convergence? Okay. So how to improve / accelerate the convergence? Again, somebody has come up with enormous innovation, and I just wanted to show you that. So let me look at these equations b and c and propose something. So rewrite b and c. So let me do the following: ui plus 1 ui minus 1 j at m plus 1. Now there was a coefficient 4 here, and instead what I'll do is I will write this as 2 plus p, and I'll give a number for p a little later. So this times uij m plus 1 plus ui plus 1 j at m plus 1. This is minus ui j minus 1 m minus, or rather plus 2 minus p uij at m minus ui j plus 1 at m. So notice what we have done. This value here, which was supposed to have a coefficient of 4, we have tweaked this a little bit and replaced that with 2 plus p. And the remaining part of it, we have taken it as a value which is known from the previous iteration. And now we can see if this makes a difference. So we can experiment with the value of p. Likewise, for the other iteration, which is ui j minus 1 m plus 2. Again, I have this so this is from the equation C, which has been modified, and this now becomes minus ui minus 1j at m plus 1 plus 2 minus p uij at m plus 1 minus a ui plus 1 j at m plus 1. So, all I have done is just modified equations C and D and replace these values 4 with 2 plus p and taken the difference on the right hand side. So, some people have experimented that can values of p lead to different values of p lead to a difference in the convergence rate, and it turns out the following. So, p equal to 2 gives us back the original method. But if I want optimal convergence, then I can use the value of p to be 2 times sine pi by k, where k is the maximum of number of rows or columns. And of course, p can vary from one step to the other. Okay. So, it turns out if I use a value of p which actually depends on the number of equations that I have, or the number of rows and columns that I have in the grid, essentially the range of I and j, then it is possible for me to get faster convergence using the ADI method. And of course, nobody stops me from varying p from one step to the other. That is what I have written here. So, I hope you have got a flavor of how these methods work for these simple differential equations, and we will discuss some more aspects of approximation in the next session. Thank you very much.